It is now.
Okay. All right, so I was asked, remember, now I don't even remember what the equation was. All right, I'm going to have to go back to the appropriate place. Hold on. So what section was it, do you remember? Oh yeah, it was like Laplace transforms and what equation number was it?
205.
4.?
205.
Okay, so we've got to go ahead of too much. Okay, so what we had originally was that the delta function, that the density that this was integral e to the minus e to the I. Oh, well, it's up here. I don't need to write it on the board. We had, sorry to be so distracted. We had the rho of x was, x and t was this Fourier, it's a sort of a Fourier Laplace transform. If the initial time zero density was just a delta function at y, and after we do the integration, we then get this expression here. So it follows then, because everything is linear, that rho, for an arbitrary distribution, initial distribution, rho of y of 0 is just the sum of all of these integrated, weighted by rho of y of 0. So in other words, if rho of x and t is that expression there, 1 over 4 pi dt to the 3/2 e to the minus x minus y squared over 4 dt. This is if rho of y and 0 is delta cube of I'm sorry, rho of x and 0 is delta cube of x minus y. So the problem is completely linear, so you can add solutions. And so for an arbitrary distribution, rho of x and t is the integral d cubed y of rho of x and t, this one in other words, rho of y and 0, which is to say an integral e to the minus x minus y squared over 4 dt, rho of y and 0, d cubed y divided by this factor 4 pi dt to the 3/2. By the way, this, which is this equation 209, this is one of the nice things about linear equations, linear differential equations, linear systems, is that if you have a solution or two solutions or a bunch of solutions, here we have a solution for every delta function at y, localized at y. So we just write the an arbitrary initial distribution rho of y and 0 is at times delta cubed of x minus y integrated d cubed y is rho of x and times 0. So we then substitute that in there, do the integration, and we get this. And the thing is, you can add solutions if the problem is linear. By the way, this is intrinsically interesting, this solution. It says that if you have diffusion, the progress of the diffusion goes as the square root of the time. That's why it's t here rather than t squared. And bacteria are so small, they're micron in size, that they can allow chemicals to diffuse from one part of a bacterium to another. They just rely upon diffusion. On the other hand, eukaryotic cells, which are much bigger, 10 times bigger in radius, so 1,000 times bigger in volume, have to have a built-in UPS or FedEx system to move chemicals around. And in particular, in our own bodies, we have some cells, nerve cells, that are like 1 meter long or longer. And so there has to be there are molecular motors that pull bags of chemicals along tracks down on nerves so that the neurotransmitter supply is replenished at the end of the nerves. All right, well that's an answer to a question that was asked, and whoa, a good catch there. If I could get another one, because terrific catch. All right, so let's go on to, is there another question before I go back to complex variable theory? Okay, so let's jump back to complex variable theory, and in particular, basically, Cauchy's integral formula. All right, first, let me remind you of the, so I'm going to, for the reminder part, I'm going to go through this on the computer screen. This is the Cauchy's integral theorem, that the integral of an analytic function around a closed contour is 0 if the function is, if the contour is entirely within the region in which the function is analytic. The next thing that we learned was Cauchy's, here, let me get rid of this thing, hide sidebar. The next thing we learned last time was Cauchy's integral formula, which follows from the integral theorem, namely that the value of an analytic function at z0 is 1 over 2 pi I times the counterclockwise integral of f of z over z minus z0, and that's integrated along any contour that goes around the point z0 once in the counterclockwise way, as long as the contour is inside the region in which the function f of z is analytic, and moreover, the region inside the contour is simply connected and the function is completely analytic in that region. So in other words, if there's no worry about analyticity, this formula always works. And it's Cauchy's integral formula, and many results in complex variable theory follow from Cauchy's integral formula in just a few steps. One of them is a formula just differentiating this expression. We get a formula for the first derivative of an analytic function, namely it's 1 over 2 pi I, the contour integral, again counterclockwise, of f of z prime over z prime minus z squared. And then if you differentiate that, you get a formula for the second derivative. And then when you do the second derivative, differentiate this, you get the 2 coming up, and the 2 appears here, and z prime minus z is then the third power. And the general formula is that the nth derivative of an analytic function at z is n factorial over 2 pi I times a contour integral of f of z prime over z prime minus z to the n plus 1. And that's an important result. And one of the amazing things about complex variable theory is that it follows immediately, essentially, from Cauchy's integral theorem and Cauchy's integral formula. So the next thing that we covered last time was harmonic functions, and remember there are the Cauchy-Riemann conditions, namely that if f is analytic and we write it in terms of a real and imaginary part, u and u plus iv, then the x derivative of u has to be the y derivative of v, and the y derivative of u has to be minus the x derivative of v. And from that it follows that uxx is minus vyy, and so uxx plus, is minus uyy, so it follows that uxx, second derivative with respect to x of u, plus the second derivative of u with respect to y, they add up to 0, which means that the two-dimensional Laplacian of the real part of an analytic function is 0. Similarly, the two-dimensional Laplacian of the imaginary part of an analytic function is 0. And that's the statement, the name we attach to things that have vanishing Laplacians is that they're harmonic. And so we say the real and imaginary parts of an analytic function are harmonic. And because they're harmonic, the real part of an analytic function cannot have a minimum or a maximum, because when you're at a minimum, hxx and hyy are both positive, or uxx plus uy and uyy would both be positive, and so this would be positive, not 0. And the same thing is true for a minimum. At a minimum, uxx would have to be, at a minimum, uxx has to be positive. I got it wrong, positive, and uyy has to be positive, so this would be positive. At a maximum, uxx is negative, uyy is negative, so the sum would be negative. And the fact that the real part is harmonic means the real part of an analytic function cannot have a minimum or a maximum in the region of analyticity. The same thing is true for the imaginary part of an analytic function. And it turns out that the electrostatic potential, and we're considering time-independent phenomena here, the electrostatic potential is a harmonic function of 3 variables, x, y, and z, because Gauss's law says that the divergence of E is 0 in regions where the charge density is 0, and E itself is minus the gradient of phi, so these two combined together say that the Laplacian of phi is 0, and so the electrostatic potential in a charge-free region is harmonic, and so if you have an electrostatic problem in which one variable is immaterial, say it doesn't depend upon z, everything just depends upon x and y, then you can identify the electrostatic potential with the real or the imaginary part of some analytic function, and that helps one solve certain problems. Or equivalently, if you have an analytic function, that gives you a zillion examples of what the electrostatic potential would be in a case that's independent, a problem that's independent of z. So if you had, for example, charges that were independent of z, you had charged cylinders or charged wires, then in the region where there are no wires, the electrostatic field would be the real or the imaginary part of some analytic function. If you now take the gradient, the two-dimensional gradient of the real part of an analytic function, and dot it into the imaginary part of an analytic function, you get ux plus vx plus uy vy, and apply the Cauchy-Riemann conditions, and you get vy vx minus vx vy, and that's 0. So the dot product of the gradient of the real part of an analytic function is perpendicular to the gradient of the imaginary part. And so if you then are identifying the real and imaginary parts with an electrostatic potential, you might say that the real part is the electrostatic potential, and then the imaginary part, or the surfaces of constant imaginary part, then are electric field lines because their gradients are perpendicular to the equipotential surfaces which are the U's. Okay. So that, I think, is where we ended things last time. So maybe, since now these are important topics covered for the first time, I'll try to explain these on the blackboard. And once again, the amazing thing is how many things in complex variable theory follow quite simply from Cauchy's theorems. So we can write an analytic function using Cauchy's integral formula as 1 over 2 pi I, and integral f of z prime dz prime over z prime minus z. And if we add and subtract z0 from the denominator there, we have 1 over 2 pi I integral f of z prime dz prime over z prime minus z0 minus z minus z0. Then if we factor that, pulling out a z prime minus z0, we have 1 over 2 pi I integral f of z prime dz prime over z prime minus z0 times 1 minus z minus z0 over z prime minus z0. Now the picture that goes with this is that we have a contour of some sort like this. It's a closed contour. Z is some point inside. I'm sorry, Z, let's see, where is Z? Oh yes, actually it's not a contour. It can, the theorem works for an arbitrary contour. But what I want to do now is actually have a nice circular contour around Z0. So we have a circle around Z0, and this is the contour that we're integrating around along, and we have a Z prime here, and Z is a point inside the contour, and we're integrating this way. And so the point is that Z prime minus Z0 is bigger than Z minus Z0. And so this ratio here is less than 1 in absolute value. This distance Z minus Z0 is less than Z prime minus Z0. And that means then that we can expand this 1 over that in a geometric series. That's one of the things that we learned in the chapter on infinite series, chapter 5. In other words, we write 1 over 1 minus Z minus Z0 over Z prime minus Z0. We can write as a sum n equals 0 to infinity of Z minus Z0 over Z prime minus Z0 to the n. And this is a geometric series, and it's uniformly and absolutely convergent because this ratio is less than 1. And so that's a really nicely convergent series. And so if we write this 1 over that as this series, then we can integrate term by term, and what we find is that f of z is this 1 over 2 pi I. This factor 1 over 2 pi I comes in, it's just absurd how often it occurs. It is then an integral over this contour. It's actually a circular contour, f of z prime over z prime minus z0, and then this is multiplied by the sum n equals 0 to infinity of z minus z0 over z prime minus z0 to the n. And we can pull out the numerator, since this is a dz prime, since it doesn't involve z prime. And then this thing is a sum n equals 0 to infinity z minus z0 to the n. That's the numerator. 1 over 2 pi I integral along this contour of f of z prime dz prime, and what's left is z prime minus z0 to the n plus 1. And on the other hand, this is an instance of Cauchy's integral formula. And so this is a sum n equals 0 to infinity z minus z0 to the n over n factorial. In other words, it's n factorial times the nth derivative of f of z at z0. And so what we've derived here is that, let me just write this as f of z, because the f of z here got sort of lost. What we've learned here then is that if you have a function that's analytic in some region, it has a power series that's uniformly and absolutely convergent, this is then it converges as long as the point z is inside a circle that is within the region of analyticity. So if the region of analyticity of the function is huge, then this power series converges uniformly and absolutely in a huge region. So this is a this means that analytic functions have marvelous Taylor series or power series. So any questions? Now, as I said, the complex variable theory is a little bit like an illustration of the, what is it called, the domino effect or something? You push one domino and it hits the next one, the next one, the next one, they all fall down. Well, it's the same thing is true of results that come just tumbling out. So suppose you have a function that's analytic in a region that includes a disk, and the disk is z less than or equal to r, and that on this disk, the absolute value of f of z is less than or equal to some m on the circle. On the circle z equals r, which is the perimeter of the disk then. And so then what we can do is we can write Cauchy's integral formula for the nth derivative at the origin. And if we take the absolute value of it, we'd see it would be less than or equal. In fact, let me write it in two steps. It would be equal to n factorial over 2 pi I, the absolute value of that integral f of z dz over z to the n plus 1, because in this case z0 is 0, and this is the absolute value. Well, that is less than or equal to n factorial over 2 pi, an integral of the absolute value of f of z, absolute value of dz, divided by absolute value of z to the n plus 1. But now the absolute value of z is r. This is less than or equal to m, and so this is equal to n factorial over 2 pi m from this, an integral r d theta over r to the n plus 1, because z is equal to r, so that's just 1 over r to the n. So this is n factorial m. The 2 pi's cancel because this integral d theta generates a 2 pi, and so this is r to the n. And so we've got a bound for the nth derivative of an analytic function at the origin. It's less than or equal to n factorial m over r to the n if the function f of z is bounded by m on a disk about the origin of radius r. This is one version of Cauchy's inequality. So we can now take this bound and go back to this expression for the Taylor series for the function f of z. And so we have the sum n equals 0 to infinity. Absolute value of, we now transfer from, this applied to, this was the case when z0 was the origin, but if we translate everything from the origin to z0, there's no change. And you see, actually, there's a typo there. So this is the function f of z, the absolute value of the function. So this is the absolute value of f of z equals that. And that then is less than or equal to, since we know what these are, that's less than or equal to m. The n factorial cancels in the Taylor series, and so we have the sum n equals 0 to infinity z minus z0 to the n over r to the n. And so this this gives us this z minus z0 to the n over r to the n is in fact if z is in fact just u. Oh my goodness, that is, yeah, z minus z0 is less than r, so this gives us a in fact, we can sum that thing. That's m over 1 minus z minus z0 over r. And so that gives us a bound for the function f of z, as well as a bound for the terms of the series. Now, Liouville made use of some of these. He imagined, let's suppose that f of z is less than or equal to m for z greater than or equal to r0. So this now, if that's true, since f in particular is continuous, it's certainly bounded for smaller values of z, if it's analytic everywhere. We can then use Cauchy's bound to say that the nth derivative at the origin is less than or equal to n factorial m over r to the n. But this thing holds for all r because f of z is less than m for all z greater than r, r0 say. So it holds for r greater than r0. But the limit, so we can choose r to be huge. We choose r to be huge, this is 0 essentially. And so this tells us that the absolute value of fn of 0 is 0 for n greater than 0. So in other words, if an analytic function is bounded everywhere, then all of its derivatives vanish except the 0th derivative, which says the function's a constant. In other words, if we could go back here and write it as a Taylor series, all these terms are 0 except the n equals 0 term, and so the function is a constant. So the bottom line here is that a bounded entire means analytic everywhere, function, a bounded entire function is a constant. That's to say f of z is equal to c for all of z. So that is Liouville's theorem. And Gauss then applied Liouville's theorem to algebra and proved the fundamental theorem of algebra. By the way, I was told, I remember a long time ago when I was a graduate student, Sidney Coleman just mentioned that centuries ago in Italy, there was some mathematician who figured out how to solve a quadratic equation, and he'd go from town to town telling people that he could solve any quadratic equation that they gave him, and people were amazed, and so they'd give him a quadratic, they bet that he couldn't, and they'd pose a quadratic equation, he'd pull out his formula, solve it, and then he'd collect the money and go on to the next town. At least that's the way I remember the story. Conceivably, it was the cubic equation. The cubic equations, though, have remarkably complicated formulas. Quadratic equation is something you can memorize easily. I've never memorized the cubic equation. And, anyway, let's get on to this fundamental theorem of algebra. What Gauss considered was this. Take any nth degree polynomial and take the reciprocal of it. So this is 1 over C0 plus C1z plus C2z squared plus dot 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 plus Cn z to the n. So that's the picture. That's what we're looking at. Now, this is one of those mathematician type proofs where you assume the thing you want to disprove. So assume if Pn of z is never 0, so suppose there's no solution, then this thing is never 0, and then you can say that f of z is entire, and you can say that the absolute value of f of z is less than or equal to 1 over Cn r0 to the n, which we can call m, for all absolute value of z greater than or equal to r0. So in other words, if you go out to huge values of z greater than or equal to some large r0, then the only thing that counts in the denominator is the largest term, whatever the biggest value of n is. And so you can ignore the lower terms, and maybe I should write an approximation here. So it's bounded essentially by that. And so that's what you would conclude. But that would mean that f of z was a constant, because a bounded entire function is a constant. But you know that f of z isn't a constant because it's 1 over a polynomial, and polynomials aren't constant. So the only way out of the contradiction is to assume that in fact f of z is not entire, and the reason it's not entire is that there's a value of z at which Pn of z vanishes. And so then the next thing you do is you say, well, let's let Pn of z equal to z minus z sub n, that's the point at which it vanishes, times some polynomial of degree n minus 1 in z. You then repeat the same argument and you find that this one has to vanish somewhere. And you pull that out, and so eventually you're able to write Pn of z is z minus z1, z minus z2, dot, 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 z minus zn. So in this way, Gauss proved that every polynomial has n roots somewhere in the complex plane. And our formula for the quadratic equation then gives us, in general, two solutions that, in nice cases, they're both real, but in general, they're complex. So this is important, and it's one of the reasons why mathematicians and even some physicists fall in love with complex variable theory, because something as hard to prove as that an arbitrary polynomial of nth degree has n roots somewhere in the complex plane is trivial proof in terms of analytic function theory. And so that's essentially amazing. So any questions? The next topic is something called Laurent series, and this is the proof of this is a little bit like what we did a moment ago on the board over there. So we start by writing using Cauchy's integral formula. So it's an integral f of z prime dz prime over z prime minus z. And we're going to go over some contour called C12. So let me sketch C12 for you. It's, if I were a foot taller, I'd write it up there, but I instead will try to write it here. So what we're imagining here is that there may be some, that f of z may lack analyticity at some points here, and maybe out here somewhere it's lacks analyticity. This would be, for example, if f of z was 1 over Pn of z, and the roots of the polynomial happen to be in here and out there. And so what we're going to try to, what we're using here is the idea that we have a region of analyticity that can be thought of as these are supposed to be two circles that are, well, let me redo the circles so that they're a little bit more what they're supposed to be. So the idea is we have two circles of different radii, about both with center at z0. And now what's the contour? The contour is we integrate along here, which I call C1. We integrate backwards here on C2. And then we connect the two like this with straight lines. And we're going to let those straight lines approach each other, in which case they would exactly cancel. And then we're going to have z be some point here. So this then is an appropriate application of Cauchy's integral formula, because the contour C12, which is sort of an absurd contour, it goes counterclockwise around z once and lies completely within a region of analyticity. And this region of analyticity is not simply connected, but this contour is such that we can move, for example, this straight line to here, and then to here, and then so forth, until finally it would be up here, and then this would be an obvious simply connected region. Actually, it is simply connected if I spoke too carelessly. This contour lies within a simply connected region because I'm splitting off this region here. And the main thing, and another way of seeing it is that you can pull this around and make it just a loop around Z. Anyway, so we have this formula, this application of the Cauchy integral formula, and now what we're going to do is, so the initial integration is up, around, backwards, around this way, around, across here, and then around here. What we're going to do first is we're going to let these two lines approach each other, in which case those integrations along the straight lines cancel each other. So we really just have two circular integrations. One is counterclockwise, and one is clockwise. So this is 1 over 2 pi I, the integral along C1, which is counterclockwise, and that's f of z prime over z prime minus z dz prime. And then because the other one is clockwise, it's 1 over 2 pi I with a minus sign. A minus sign if we do the thing. Now the contour C2 is going to be counterclockwise if we put in the minus sign. So this is f of z prime dz prime over z prime minus z. So the C2 contour is really counterclockwise. That's why there's a minus sign here. But it's the inner circle. And now what we're going to do is we're going to write this as a double prime. And then what we're going to do is notice that z double prime minus z0 over z minus z0 is less than 1. So the z double prime is on this contour here. So d double prime minus z0 is less than z minus z0. That's because z is inside the annulus between the smaller circle C2 and the bigger circle C1. And also z minus z0 over z prime minus z0 in absolute value is less than 1. And that's because z minus z0 is less than z prime minus z0, z prime being on C1. And so then if we add and subtract z0 from both denominators here and factorize, what we'd have would be 1 over 2 pi I factor, I shouldn't say factorize. Integral C1 f of z prime dz prime over z prime minus z0, and I think I'll just factor on the fly here. It's then 1 minus z minus z0 over z prime minus z0. That's the first term. And then this second one will do the same thing, but I'm going to absorb the minus sign into the denominator. And if we do that, what we have is plus 1 over 2 pi I integral f of z double prime dz double prime over, and this would be then z minus z0 times 1 minus z double prime minus z0 over z minus z0. Actually, I don't know why I wrote that as, why I put those parentheses in there. It's kind of silly. Okay, so that's the difference of the two, and this is all the C2. Both are circular counterclockwise contours. And so now we just apply the fact that this is less than 1 and this is less than 1, and so we can expand these as geometric series. And what we get then is that f of z is a sum n equals 0 to infinity, z minus z0 to the n, 1 over 2 pi I, integral c1 f of z prime dz prime over z prime minus z0 to the n plus 1 plus the sum, let's say m equals 0 to infinity, 1 over z minus z0 to the m plus 1, 1 over 2 pi I, integral c2, z double prime minus z0 to the m, f of z double prime dz double prime. So there are a lot of primes and terms here, but I think I've written down everything correctly. Okay, so what we do next is we let these two circles approach each other, and since we stay within the realm of analyticity, there's no change when we do that, and so we just have one circle that we're integrating over. And so finally what we get then, and we do something else. You know, when it comes to discrete counting, there's always a little bit of confusion. So what we do here is we set m equal to minus n minus 1, or n equal to minus m minus 1. And so that means that in this sum, n is going from minus 1 to minus infinity. Or equivalently, the two sums can be combined, and n is going from minus infinity to plus infinity. So what we have then is that f of z is a sum n equals minus infinity to plus infinity. And it's z minus z0 to the n times 1 over 2 pi I, the integral over the circle C that the two of them are merged into, of f of z dz over z minus z0 to the n plus 1. And so that means we can, if we want, write this as n equals minus infinity to plus infinity. It's often written as a sub n of z0, z minus z0 to the n, that's this term. The a sub n of z0 is what's left over, namely a sub n of z0 is equal to this 1 over 2 pi I times this integral. This is called a Laurent series, and so the requirement then is that these a sub n's are given by this contour integral. The contour goes goes through an annulus in which the function's analytic, and inside and outside there are singularities, but in the region, in the annulus, the function's analytic. So this is a very general representation of a function of a complex variable, but it's analytic in a certain annulus. If it's analytic in an annulus, then, but not analytic inside the annulus, then you have to include in principle all the negative powers, z minus z0 to negative powers. Now, typically, you don't have to go all the way to minus infinity, but sometimes you do. You do if the function has an essential singularity. So that's some terminology that I should mention. Let me write down this a sub n formula again on that board there. In other words, we're going to say that a sub n of z0 is 1 over 2 pi I integral along a contour around z0, of course, of f of z dz over z minus z0 to the n plus 1. And these n's are not all positive. They can be arbitrarily negative. And this is there's a particular, and for this, what we can say is that f of z is a sum n equals minus infinity to plus infinity a n of z0, z minus z0 to the n. No, I didn't quite do that. Okay. The simplest case of this is a sub minus 1 of z0, and that is just 1 over 2 pi I times the integral of f of z dz around the point z0. Now, this, if there were no singularities, if f was entire, or if f were analytic inside this contour C, then this would be 0. But we're considering the case where this is the contour C, and there are some singularities here and some singularities outside. And so then this is called the residue. And many treatments of complex theory, variable theory, make a big deal of residues and of something called the residue theorem. I don't quite know why. Anyway, as I said, it's often true for nice functions that you don't start at minus infinity. You start at some minus L and then go on to positive values. When you can just start at minus L, then there are two ways of computing these a sub n's. You can do this integral, or if you have a nice expression for f of z, you can just say that f of z is some sum n equals minus L to infinity an of z0, z minus z0 to the n, and then you can pick off a sub minus L as the limit. A sub minus L of z0 is the limit of z minus z0 to the L times f of z. And you let z approach z0. All the higher terms are 0, become 0 or epsilon to some high positive power. They're 0. The a sub minus L term is a sub minus L of z0. This and that cancel, and so in the limit, it's just, even as you take the limit, it's just 1 all the time, and all the other terms are 0. So that's another way of forming the not simply the residue, but the arbitrary coefficient. But that is assuming that you know that you have a formula for s of z. Of course, if you have a formula for f of z, then you might not need this at all to begin with. All right, some common terminology that you already know. A function that's analytic everywhere is entire, and entire functions have no singularities anywhere. Now, some people say that the point as z goes to infinity, typically a function that's entire will, of course, if it's not a constant, it will become arbitrarily large as z goes to infinity in one direction or another. And so people say, well, there's a singularity at the point at infinity. It always bothered me that it was called the point at infinity because, after all, as you let the absolute value of z goes to infinity, you have a whole, it's really going to infinity on a huge circle. And it might be very large at one point on the circle, very small at some other point. Anyway, it's called the point of infinity for some reason. We say that a function has an isolated singularity, and that's what I essentially was assuming there by writing those dots. So isolated singularity at z0 if f of z is analytic in disk about z0 but not at z0. So in other words, it's and an example of that is f of z equal to 1 over z minus z0 to some positive power, integral positive power. If it's 1 over, if n is 1, then it says, this is said to be a pole of order n. And so a simple pole is when n is equal to 1. And if you have a function that's analytic apart from poles, it's said to be meromorphic. So meromorphic is analytic except for poles. Okay. Now, essential singularities are really remarkable things. Let me give you an example of an essential singularity. E to the 1 over z. That's a function that has an essential singularity at z equal to 0. And there's a theorem due to Picard, which is that suppose a function has an essential, if f of z has an essential singularity at w, then It's really amazing. In every disk about W, no matter how small the disk, f of z takes on every complex value, with at most one exception, an infinite number of times. So in other words, then inside every disk of arbitrarily small radius, you can say f of z is equal to whatever you want, let us call it z star, for infinitely many z's in the disk. And the exception is that it works for every value, every complex number z star except for 1. So it's again one of those remarkable things in these things sometimes occur in physics, or at least are somewhat like, something like this occurs in physics in various ways, various times. But I don't think I should go on with that. All right, so analytic continuation. The idea here is that we can write a function as a Taylor series. We saw that z minus z0 to the n over n factorial, the nth derivative at z0. So we can do that out to some radius r about z0. And this radius r we can extend up to the nearest singularity. So suppose this is the nearest singularity to z0, and so r is that big, and so r is just inside that singularity. On the other hand, if we go over here and we pick a point here inside the region of analyticity, we can form a Taylor series about this point. And typically, that Taylor series will look something like this. I'm just speaking qualitatively here. Quantitatively, but I'm waving hands. So if you do that Taylor series expansion about this point, what you see is you now have extended the region of analyticity. It's now not just this circle of this disk of radius r, but it also has this bump. And then you could do the same thing over here, and then you might have something like that. And then once you've done that, you can try a point here and do a power series expansion. This is called analytic continuation. There is a famous example of it, and since I've run out of backboard space, let me see if I can show it to you, and it's the gamma function. So let's see, we want to get to 108. Battery. Oh Lord! We connected it, but didn't turn the charger on. Okay, the gamma function. So let me kill the light so you can see this a little bit better. Remember that the gamma function is defined in this way, and perversely is not z factorial, but is z minus 1 factorial. And if you look at this expression here, you see that z is analytic in the right half plane, rz, real part of z greater than 0. And that's because if the real part of z is greater than 0, then this 1 over t singularity is 1 over, it's not quite 1 over t, it's softer than 1 over t, and so the integral converges. But then you can use successively this expression to write gamma of z as 1 over z times gamma of z plus 1, and so on and so forth. And the last expression then gives you get 3 pole terms, 1 at 0, 1 at minus 1, 1 at minus 2. But then you have gamma of z plus 3. But this is analytic for the real part of z greater than minus 3. So what we've done here, very simply, is we've analytically continued gamma of z from the right half plane to the half plane to the right of minus 3. And then we can continue and do the same thing for an arbitrarily, in other words, we could do it to the right of minus 9 or the right of minus 1,000,000. And the result is that we find that we can analytically continue the gamma function so that it is analytic everywhere except at z equal to 0 and at z equal to the negative integers. Minus 1, minus 2, minus 3, and so forth. So that's an example of analytic continuation from the right half plane to the whole complex plane minus the negative integers and 0. And so that's an example of analytic continuation that's quite remarkable and is part of the stuff that you guys are worried about because of the midterm exam. All right, well, we're out of time, so I think we'll stop at this point and pick up calculus of residues on, well, it's not going to be Thursday, it'll be next Tuesday. So Wednesday is tomorrow. I'm going to have the problem session. I'm going to do class. I'm going to do the problem session. Is anybody coming? I mean, maybe everybody is skipping. Is anybody coming tomorrow? All right, I see one person nodding, so we'll at least have a tutorial, a private tutorial. But anybody who wants to come, of course, is welcome. So there's class tomorrow, but there's no class Thursday and Friday. The next regular class at 466 will be Tuesday. Okay, so we might as well turn it off.